The cosmos holds a profound and deceptive silence. Yet within that quiet, our most powerful telescopes have begun to capture something astonishing. Strange, unexplained signals are emerging from the turbulent clouds of interstellar plasma, the very fabric of space itself. These are not simple messages, but complex cosmic phenomena that defy our current understanding of physics. By the end of this journey, you will be familiar with 25 of the universe's most compelling mysteries. We will investigate a signal so powerful it was once considered our best candidate for alien contact, and explore bursts of energy that appear and vanish in a millisecond, leaving astronomers utterly baffled. What hidden force do you believe is orchestrating these cosmic whispers? That profound silence was broken on one unforgettable night in August 1977. An astronomer named Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope when he saw a string of letters and numbers so significant he circled them in red pen and wrote one word beside them. Wow, the signal was a powerful, focused burst of radio energy 30 times stronger than the background noise, and it lasted for a full 72 seconds. For decades, it stood as our most tantalizing hint that we might not be alone, a singular event that perfectly matched what scientists predicted an interstellar message would look like. But what if the source was not a civilization, but the cosmos itself playing a trick on us? A compelling new theory suggests the WOW signal might not have been a direct broadcast. Instead, it could have been a much weaker signal from a distant, natural cosmic event, perhaps even a random blip that was dramatically amplified. The culprit, a dense, drifting cloud of interstellar plasma. This ionized gas, when shaped in just the right way, can act as a natural lens in space, bending and focusing radio waves just like a magnifying glass concentrates sunlight. A faint signal passing through such a cosmic lens could be intensified into the stunningly powerful spike that stunned Jerry Amon. This idea reframes the entire mystery. The debate is no longer a simple choice between aliens or noise. It is a deeper investigation into the architecture of space itself. Could the vast, turbulent clouds that drift between the stars be capable of such precise, fleeting amplification? Or does the unique character of the WOW signal still point to a more deliberate origin? The search for an answer continues, but the question itself has fundamentally changed, forcing us to look not just for senders, but for the invisible lenses that might be focusing their whispers into momentary shouts. Decades later, the WOW signal still resists a simple answer, but our tools for investigation have grown far more sophisticated. Modern supercomputers now allow us to model the behavior of interstellar plasma with incredible detail. These new simulations reveal that a cloud of this ionized gas, if it were turbulent and moving at just the right speed, could do more than just amplify a signal. It could also filter it, sculpting a random burst of cosmic noise into a sharp, narrowband signal that appears artificial. The very characteristic that made the WOW signal so compelling, its precise frequency, might not be a sign of intelligence, but a signature of a complex natural lens. This plasma lens would be a temporary and unstable structure, constantly shifting and changing. This offers a potential explanation for the signal's most haunting quality, its utter silence ever since. We have pointed our most powerful dishes at that same patch of sky for years, listening intently, and heard nothing. If the signal was a product of a fleeting cosmic alignment, a momentary focus by a passing plasma cloud, then it was a 1 in a billion event. The lens formed, it focused a faint background whisper into a shout we could hear, and then it dissolved back into the chaotic ocean of space. We happened to be listening at the exact moment the universe's magnifying glass passed over a faint star. This does not make the WOW signal any less profound. It simply transforms its mystery from a question of who to a question of how. The cosmos is filled with these invisible, shifting structures, and their ability to warp and focus light and radio waves is only beginning to be understood. They are the ghostly architecture of the void, capable of creating illusions and miracles that challenge our perception. The ghostly architecture of space does not only create illusions, it can also unleash unimaginable violence. In 2007, astronomer Duncan Lorimer and his student were sifting through archived data from a Parkes radio telescope survey of the Magellanic Clouds when they found something that should not have been there. It was a single burst of radio waves, a blast so powerful and so brief it was over in 5 milliseconds. But in that sliver of time, it released more energy than our sun emits over 300,000 years. The initial reaction was not excitement, but deep skepticism. The signal was so far outside any known phenomenon that the most logical explanation seemed to be a glitch, a simple error in the telescope's own electronics. It was dismissed as terrestrial interference and nearly forgotten, a ghost in the machine. Yet Lorimer was not convinced. He meticulously ruled out every possible source of human-made noise, from passing satellites to ground-based radar. The signal was real, and it had come from deep space. This single data point, now known as the Lorimer Burst, shattered our understanding of cosmic energy. It was the first recognized fast radio burst, a new class of astronomical event. The leading theory to explain such a staggering release of energy points directly back to the plasma clouds that drift between the stars. Imagine a cataclysm of almost biblical proportions, a super-dense object like a neutron star collapsing into a black hole, or two such stars merging in a violent embrace. This event would unleash a titanic shockwave, a blast front that plows through the surrounding cloud of interstellar plasma at nearly the speed of light. The interaction between this relativistic shock and the magnetized plasma is like a cosmic bell being struck, generating a coherent, lighthouse-like flash of radio waves that we see as a brief, impossibly bright burst. The Lorimer Burst was not a focused message or a steady beacon. It was the death cry of a star, filtered and broadcast across the universe by the very medium it was tearing through. In that 5-millisecond flash, we witnessed the echo of a cosmic catastrophe, proving that the silent plasma between the stars can become the amplifier for the universe's most violent symphonies. The universe's most violent symphonies are not always a single crashing chord. Sometimes they are a recurring theme. After the initial shock of the Lorimer Burst faded, astronomers assumed all fast radio bursts were one-off cataclysms, the final, explosive signatures of events that could not happen twice. Then in 2016, they found the repeater. Known as FRB 121102, this signal shattered the single blast model. It did not just flash once and vanish into silence. It flashed again and again and again, sending powerful millisecond bursts from a tiny, dwarf galaxy 3 billion light-years away. Here was a source of cosmic energy that was not destroying itself but somehow persisting. This was no ordinary stellar corpse. The repeater's behavior pointed directly to a specific and terrifyingly powerful type of neutron star called a magnetar. Imagine the core of a giant star collapsed into a sphere just a dozen miles across, yet possessing a density so immense that a single teaspoon of its material would weigh billions of tons. Now amplify its magnetic field to a level 1,000 trillion times stronger than Earth's. You have a magnetar, a cosmic powerhouse whose crust can crack under magnetic stress, releasing starquakes that ripple through its surroundings. But a lone magnetar was not enough to explain the repeater. The key to its persistent, repeating nature lies in what surrounds it. Astronomers discovered that FRB 121102 is embedded within a thick, turbulent nebula of magnetized plasma. This is not a calm, empty void. It is a persistent, churning storm of particles and magnetic fields, a cradle of chaos forged by the magnetar's own violent youth. Think of the magnetar as a frantic bell ringer trapped inside a resonant metal chamber. Each time the magnetar's crust shifts or its magnetic field lines snap and reconnect, it sends a shock wave out into this surrounding plasma nebula. The nebula itself then acts as both an amplifier and a filter. It takes the raw, chaotic energy of the starquake and sculpts it into the coherent, intensely bright radio flashes we detect. The nebula's own swirling, dynamic magnetic fields can focus these bursts, and its dense plasma can even cause the signals to scatter and arrive at slightly different times, creating a complex fingerprint. This intricate dance between a stable yet violently active central engine and its volatile environment solves the mystery of repetition. The magnetar provides the power over and over, and the plasma nebula provides the lens and the speaker, broadcasting the outbursts across the cosmos. This means we are not listening to a series of final deaths, but to the tumultuous, ongoing life of a cosmic monster, a reality far stranger than any single destructive blast. Deep within the heart of our own galaxy, a different kind of signal echoes through the dark. These are not the sharp, millisecond cracks of fast radio bursts, but something slower and more resonant, like distant cosmic thunder. Astronomers call them low-frequency radio booms. They emanate from the direction of the Milky Way's turbulent core, a place dominated by our supermassive black hole, Sagittarius A star. This colossal object, with a mass 4 million times that of our Sun, is not a silent predator. It is the conductor of a chaotic orchestra, and the instrument it plays is the vast, magnetized ocean of plasma that swirls around it. The leading explanation for these mysterious booms lies in the violent interactions between this gravitational giant and its volatile environment. Picture the immense disk of superheated gas and plasma that orbits the black hole. This is not a smooth, flowing river of matter, but a churning, turbulent maelstrom. Clumps of plasma, larger than entire solar systems, constantly collide and merge. Magnetic field lines within this soup become twisted and strained, storing immense energy like a wound-up spring. When the stress becomes too great, these field lines can snap and violently reconnect, a process that acts like a cosmic short circuit. This magnetic reconnection unleashes a titanic explosion, a burst of energy that ripples outward through the surrounding plasma. This explosion is the boom. It is the sound of space itself ringing, a low-frequency shockwave that we can detect as a powerful surge in radio waves. It is not a single event, but a recurring phenomenon, a testament to the continuous, stormy weather at our galactic center. Each boom is a direct echo of the black hole's influence, a reminder that even when it is not actively feeding, its immense gravity stirs the pot, creating a dynamic and violent environment where the very fabric of space and plasma conspires to create thunder without sound. The cosmic thunder from our galactic center demonstrates the raw power of plasma. But what happens when that same turbulent medium distorts a signal so perfectly it mimics the very thing we are searching for? This brings us to one of the most perplexing enigmas in the search for extraterrestrial intelligence, a signal known only by its catalog number, SETI 02+14A. For a brief, hopeful period, this was a prime candidate. It was a persistent, narrow-band radio signal, the kind our technology produces, and it seemed to originate from a point in the void between the constellations Pisces and Aries. Yet it was deeply strange from the start. Its frequency was not stable. It drifted, wandering across a tiny sliver of the radio spectrum in a way that was difficult to explain. If this was a transmission from a planet orbiting a distant star, its motion should have created a predictable Doppler shift, a smooth and regular change in frequency. The signal from SETI 02+14 did not obey this rule. Its drift was erratic, almost jittery, as if the source itself was trembling. The most compelling explanation for this bizarre behavior lies not with a trembling transmitter, but with the very fabric of space the signal had to traverse. Imagine this radio wave embarking on a 3 billion-year journey to reach us. It does not fly through a perfect vacuum. Instead, it must pass through countless sheets and filaments of interstellar plasma, each one a turbulent, magnetized sea of charged particles. These are not static walls. They ripple, they swirl, they expand and contract. As the signal pierces each successive plasma sheet, its path is subtly bent and its frequency is minutely shifted. A single, stable cloud might create a consistent distortion, but multiple, independently moving clouds create a chaotic lens. The signal is not just bent once. It is jostled, squeezed, and scattered over its immense journey. The result is a cumulative distortion that makes the signal appear to drift erratically. The original transmission could have been a clean, steady tone, a deliberate beacon. By the time it fought its way through the cosmic storm of interstellar plasma, it arrived at our telescopes as a wavering, uncertain whisper. This transforms the mystery of SETI 02 + 14A. We are likely not hearing a failed attempt at contact. We are hearing a profound demonstration of the universe's noise. The space between stars is not empty. It is a dynamic, layered filter, and sometimes it can sculpt random noise into a pattern that perfectly matches our expectations, only to betray its own natural origin through the subtle, erratic dance it imposes. A sun-like star 164 light-years away suddenly seemed to be calling us. In 2016, a Russian radio telescope detected a strong, narrowband signal apparently originating from the star HD 164595. For a moment, the possibility was electrifying. Here was a star remarkably similar to our own sun, and from its direction came a radio pulse that fit the profile of a technological broadcast. The news sparked a brief but intense wave of excitement and speculation. Yet the signal was never heard again. The prevailing scientific explanation is a sobering lesson in cosmic irony. The signal was almost certainly our own. The frequency of the transmission was a known one, used by military satellites and other human technologies. The most plausible scenario is that the Russian telescope intercepted a terrestrial broadcast that had bounced off a piece of space debris orbiting our planet. A human-made signal, reflected by human-made junk, created a perfect illusion of an interstellar message. It was a cosmic echo of ourselves, but there remains a more exotic, fringe possibility that connects this mystery directly to the universe's invisible lenses. What if the signal was not a reflection but an amplification? Imagine a faint, random burst of radio noise from deep space, perhaps from a distant quasar or a stellar flare. On its long journey to Earth, this insignificant whisper passes through a drifting cloud of interstellar plasma. If that cloud were shaped like a natural lens, it could have focused and intensified the signal, transforming it into the powerful, seemingly artificial spike that the Russian telescope detected. This plasma lens would have been a fleeting structure, forming and dissolving in the void, which would explain why the signal was never repeated. We were not hearing an echo of our own technology, but a momentary mirage created by the cosmos itself. This idea, while not the mainstream view, forces us to confront a profound question. As our search for intelligent life grows more sophisticated, how many of the signals we so eagerly chase are not messages at all, but merely the universe playing tricks with its own turbulent, magnifying clouds? The case of HD 164595 serves as a dual cautionary tale, warning us to look for reflections in our own backyard while also reminding us that the empty space between the stars is far from empty and is capable of creating convincing illusions from the faintest of cosmic whispers. For years, astronomers tracking fast radio bursts faced a confounding problem: signals that seemed to come from deep space but were actually born right here on Earth. They named these false alarms peritons after a mythical stag that could fly. A periton looked almost identical to a cosmic FRB in every way, a brief, intense burst of radio waves. But there was one crucial difference. While true FRBs show a telltale smear across frequencies, a fingerprint caused by their long journey through interstellar plasma, peritons did not. They were local, and their source was a complete mystery for years. The breakthrough in this cosmic detective story came from an unlikely place, the kitchen. Researchers at the Parkes Observatory in Australia noticed that these suspicious signals only appeared during weekday working hours. This pointed to a human-made source somewhere on the observatory grounds. The investigation narrowed, and the culprit was finally caught. It was a microwave oven in the staff kitchen. The peritons were generated when someone opened the oven door before the timer had fully finished. The magnetron, the device that produces the microwaves, released a final, quick burst of radiation that the incredibly sensitive radio telescope could easily pick up. This mundane explanation solved the majority of the periton cases, a humbling reminder that our search for cosmic wonders is always vulnerable to terrestrial interference. Yet the story does not end with a slammed oven door. A few of these periton signals have exhibited strange properties that do not fit the microwave oven profile perfectly. Could some unsolved peritons be something else entirely? A tantalizing possibility points not to the kitchen but upwards to the very edge of our atmosphere. The ionosphere is a turbulent layer of plasma, charged particles energized by the sun's radiation. Under certain conditions, perhaps during intense solar storms or through interactions with cosmic rays, this plasma could theoretically generate its own brief, powerful radio bursts. These would be true atmospheric phenomena, a natural flicker from the shimmering plasma shield that surrounds our world. They would be local, explaining the lack of an interstellar fingerprint, but also natural, a whisper from the turbulent ocean of charged particles right above our heads. So while most peritons are a lesson in checking our appliances first, a few might still be a genuine, if far closer, cosmic mystery, a demonstration that plasma can create its own fleeting signals even within the confines of our own sky. The hunt for fast radio bursts was once a painstakingly slow endeavor, with discoveries separated by years of patient waiting. That era ended abruptly with the arrival of a new giant on the scene. Perched in the mountains of British Columbia, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is not a traditional single-dish telescope. It is a sprawling array of 4 massive, stationary half-pipes, a metal forest designed to scan the entire northern sky every single day. This relentless gaze has turned a trickle of FRB discoveries into a flash flood, cataloging hundreds of these mysterious bursts and fundamentally reshaping the mystery. With so many new signals to analyze, astronomers could finally move beyond studying individual events and begin to see the larger picture. They looked for patterns in the data, mapping the cosmic addresses of these bursts across the universe. A startling trend emerged. A significant number of these incredibly energetic events seem to originate from quiet, unremarkable regions of space, often far from the dense hearts of galaxies. This was a direct challenge to the idea that all FRBs were born from cataclysmic mergers or the violent deaths of massive stars, events you would expect to find in the bustling stellar nurseries of galactic cores. So what cosmic environment could possibly power these immense explosions in the relative quiet of deep intergalactic space? The answer points once again to the hidden reservoirs of the cosmos. These quiet regions are not truly empty. They are vast halos of diffuse, million-degree gas and magnetized plasma that surround entire galaxies. This interstellar plasma, heated by ancient galactic winds and supernova shocks, forms a colossal, invisible atmosphere. Within this seething ocean of charged particles, immense but subtle processes could be at work. Magnetic field lines stretched across light years could slowly build up energy until they snap in a massive reconnection event, a silent short circuit on a cosmic scale. Alternatively, a shock wave from a long-past explosion, still traveling through this tenuous plasma halo, could suddenly interact with a denser pocket of gas, triggering a brilliant radio flash. CHIME's statistical treasure trove suggests that fast radio bursts are not one single type of phenomenon. Instead, they are a diverse family of cosmic flashes, with many likely being the signature of this diffuse interstellar plasma itself, suddenly and violently releasing energy that has been building for eons. The universe's most powerful flashes may not always come from its most dramatic objects, but from the quiet, simmering energy stored in the space between everything else. The sheer number of new fast radio bursts revealed a stunning diversity, but one burst in particular stood out for its unique fingerprint. FRB 190523 arrived from a massive, sedate galaxy nearly 8 billion light-years away, and it carried a profound secret in its signal. Astronomers measured its dispersion, the subtle smearing of the burst across different radio frequencies, and the value was extraordinarily high. This dispersion is the key to understanding the journey the signal took. As a radio wave travels through the cosmos, it does not fly through a perfect vacuum. It plows through a diffuse ocean of free-floating electrons, the charged particles that make up interstellar and intergalactic plasma. These electrons act like a cosmic prism for radio waves. The lower frequency components of the burst interact with the electrons more strongly than the higher frequencies, causing them to slow down just a fraction more. Over a journey of billions of light-years, this tiny delay adds up, stretching the brief millisecond pulse into a recognizable smear across the radio band. The greater the dispersion measure, the more electrons the signal has encountered along its path. The extreme dispersion of FRB 190523 told a dramatic story. It meant that this single burst had passed through an immense amount of ionized material, a staggering quantity of plasma that was far greater than what most other bursts had encountered. This was not just a measurement of the burst itself, but a measurement of the universe's hidden structure. The signal had to traverse the turbulent plasma halos of its own host galaxy, then the even more immense and diffuse plasma that fills the space between galaxies in a massive cluster, and finally the cumulative fog of countless other plasma filaments in the intergalactic void. The extreme value was like a cosmic odometer reading, revealing that the path to Earth was particularly dense with this charged material. It provided some of the most compelling direct evidence for the vast, web-like reservoirs of hot, ionized gas that cosmological models predict should exist, the very material that is notoriously difficult to detect by any other means. This one fleeting burst of radio energy became a precise probe, illuminating the invisible architecture of the cosmos and confirming that the spaces we think of as empty are, in fact, filled with a seething, tenuous ocean of plasma that shapes everything that passes through it. That same invisible ocean of plasma, which can amplify and distort signals, can also silence the cosmos's most reliable timekeepers. Pulsars are the rapidly spinning, ultra-dense cores of dead stars, and for decades they have been celebrated as the universe's most precise lighthouses, sending out beams of radio waves with metronomic regularity. Yet sometimes these cosmic clocks simply stop ticking. Astronomers watch in bewilderment as a pulsar's steady pulse suddenly vanishes for a few rotations, or sometimes for minutes or even hours, in a phenomenon known as nulling. At other times, the pulsar doesn't go silent but abruptly changes its rhythm, switching to a different pattern of brightness or pulse shape in a dramatic mode change. These are not instrument glitches, they are real, unexplained failures in a stellar engine we thought we understood. The secret to these disruptions lies not in the solid crust of the neutron star, but in the seething, magnetized storm of plasma that surrounds it. A pulsar's powerful beam is not generated by the star itself, but by a complex dance within its magnetosphere, a region dominated by intense magnetic fields and a soup of charged particles ripped from the star's surface. Think of this plasma environment as the lighthouse's lamp and its intricate wiring. For the beam to shine so steadily, this system must be in a perfect, stable equilibrium. But what if that balance is shattered? One leading theory suggests that the plasma itself can suddenly become unstable. Dense pockets of charged particles might build up and then collapse, short-circuiting the mechanism that generates the radio waves and causing the pulse to null out. It is like an overloaded power grid succumbing to a blackout. The energy is still there, but the delivery system has temporarily failed. Another compelling idea points to an external intruder. The space between stars is not empty. A faint, wandering cloud of interstellar plasma could drift directly through the pulsar's magnetosphere. This alien cloud would not be destroyed. Instead, it would violently disrupt the pulsar's carefully ordered magnetic fields. The intruding plasma's own magnetic signature would clash with the pulsar's, tangling the field lines and effectively throwing a wrench into the works of the cosmic lighthouse. The beam would stutter, change, or vanish entirely until the cloud passed by, and the magnetosphere could re-establish its stable state. These sudden silences and shifts are more than just cosmic curiosities. They are vital clues. By studying how and when a pulsar nulls or changes mode, we are essentially performing a remote diagnosis of the most extreme physical environment in the universe, a place where gravity and magnetism rule over a sea of lightning. Each unexpected quiet moment is a message telling us that even the steadiest beacons in the sky are at the mercy of the invisible, turbulent plasma that permeates all of space. A ghost once spoke to NASA in its own language. The sprawling antennas of the Deep Space Network, the very same system used to command the Voyager probes at the edge of our solar system, intercepted a bizarre and powerful signal. It was a structured digital transmission, a stream of ones and zeros that perfectly mimicked the data format of a human spacecraft. For a heart-stopping moment, the terrifying and thrilling possibility emerged that it was a signal from an unknown, lost probe or something far stranger. Yet no human craft was anywhere near the signal's apparent point of origin. The mystery deepened until investigators landed on a far more natural, yet equally violent explanation. The source was not a piece of forgotten technology, but a storm of plasma within our own solar system. The sun constantly exhales a stream of charged particles known as the solar wind, and when this wind interacts with the magnetic fields of planets or even with itself, it can create concentrated knots of incredibly energetic plasma. Under the right conditions, these knots can discharge their energy not as a simple burst of static, but as a coherent, structured radio pulse. The complex, twisting magnetic fields within the plasma itself can act like a natural computer, encoding the energy release into a surprisingly organized digital pattern. Think of it as a lightning strike inside a superheated, magnetized cloud, but a lightning strike that forges a momentary, perfect imitation of a synthetic code. The Deep Space Network's glitch was not a message from the void, but a stunning demonstration of nature's ability to replicate order from chaos. It reveals that the building blocks of a recognizable signal, the very ones we associate with intelligence, can emerge spontaneously from the raw, turbulent physics of our own cosmic backyard. This forces a humbling realization. If our own sun's plasma can impersonate a spacecraft, how many other cosmic whispers that seem to carry a message are merely the universe speaking in its own elemental and deeply deceptive tongue? A star 1,400 light-years away presented a mystery so bizarre it demanded an extraordinary explanation. Known as Tabby's star, its light would sometimes dip by a staggering 22%, a fluctuation far too extreme to be caused by an ordinary planet. For a time, the most tantalizing theory was that an alien megastructure, a vast swarm of energy-collecting panels, was orbiting the star and blocking its light. This idea sparked one of the most intense hunts in modern astronomy, as the world's most powerful radio telescopes were aimed at this single point of light, listening for the hum of a Type II civilization at work. The result was a profound and telling silence. Not a single whisper of artificial radio transmission was ever found. The absence of a signal became a signal in itself, forcing a re-evaluation of the entire mystery. If it was not a megastructure, what could possibly cause such dramatic, irregular dimming without producing any technological radio noise? The answer appears to lie in a natural, if exotic, cosmic environment. The most consistent observations now point to a vast, swirling cloud of dust and plasma that surrounds the star. This is not a uniform cloud, but a chaotic field of debris, possibly the remnants of a shattered moon or a colossal family of comets, all held in a tumultuous dance by the star's gravity. Within this cloud, countless tiny particles of dust and larger, rocky fragments orbit in a dense, uneven swarm. When these fragments pass in front of the star, they block its light in those strange, deep dips we observe. But the plasma component of this cloud adds another crucial layer to the mystery. This ionized gas mingled with the dust would be highly effective at absorbing and scattering radio waves. Any attempt to transmit a signal from a planet within that system, or any leakage from technology on its surface, would have to fight its way out through this churning, electrically charged fog. The radio waves would be absorbed, their energy converted to heat or scattered in a million different directions, their coherent message reduced to meaningless static long before it reached our telescopes. The profound silence from Tabby's star is not evidence of an empty system. It is the signature of a system cloaked in its own turbulent shroud. The very phenomenon that dims its light also acts as a cosmic radio shield, demonstrating that a natural veil of dust and plasma can render a world utterly silent, hiding it not in darkness but in a storm of its own making. Our nearest stellar neighbor sent a whisper that stopped the world. In late 2020, a team with the Breakthrough Listen project detected a narrowband radio signal, designated BLC-1, that seemed to originate from the Proxima Centauri system. This was not a random patch of deep space. This was a star just over 4 light-years away, a star known to host at least one rocky planet within its habitable zone. The signal itself was a tantalizing candidate. It was a pure, unmodulated tone at 982 MHz, a frequency typically quiet on Earth, making it less likely to be simple interference. It drifted in a way that loosely suggested a planetary origin, and it persisted for over 5 hours. For a brief, electrifying moment, the possibility was real. We might have heard a technological signature from the cosmic backyard. The subsequent investigation was a masterclass in scientific skepticism. The team did not announce a discovery. They embarked on a meticulous process of elimination, hunting for any possible terrestrial explanation. They checked for satellites, for aircraft, for any human technology that could have mimicked the signal. The most telling clue emerged when they pointed other telescopes at Proxima Centauri. The signal was never heard again. The most plausible conclusion is that BLC-1 was a product of human technology, a form of radio interference that was so subtle and complex it perfectly impersonated an interstellar broadcast. Yet, nestled within this sobering explanation, a faint, exotic possibility still flickers. Proxima Centauri is a violent red dwarf star, prone to immense flares that can bathe its planets in deadly radiation. These stellar eruptions are colossal explosions of magnetized plasma. Could a signal, perhaps even a natural radio burst generated by the flare itself, have been scattered and distorted as it passed through this tempest of stellar plasma? The chaotic magnetic fields within an erupting plasma cloud could have twisted a simple, broadband burst of stellar static into a narrow, focused spike that just happened to look artificial to our instruments. The chances are incredibly slim, but the idea remains. It suggests that the most disappointing false alarms might still be hiding a deeper truth. The violent plasma storms around other stars could be sculpting their own cosmic mirages, creating signals that wink into existence for just a few hours, born from stellar fury and scattered into a perfect, deceptive shape before vanishing forever. While we listen for whispers in the radio static, the cosmos is screaming in infrared. Telescopes like Spitzer have captured a different kind of signal altogether, not brief bursts of radio energy, but strange, fluctuating waves of heat radiating from the dark spaces between the stars. These are not the steady glow of a calm nebula. They are violent, shifting infrared emissions that pulse and change unpredictably. The source of this cosmic heat is not a single star, but something far more immense and chaotic. Picture two colossal clouds of interstellar gas and plasma, each light years across, drifting into one another in a slow-motion collision of almost unimaginable scale. Within these clouds are pockets of gas compressed to incredible densities, triggering the birth of new, massive stars. These stellar infants are furious, and they flood their surroundings with intense ultraviolet radiation. This radiation strikes the vast sea of hydrogen molecules and dust within the plasma cloud, causing them to vibrate intensely and release their pent-up energy as a powerful, shimmering infrared glow. The fluctuations we detect are the echoes of this violent stellar nursery. Every time a new star ignites or when a shockwave from a supernova ripples through the cloud, the thermal emission spikes. It is the sound of a cosmic forge, its infrared scream modulated by the relentless hammer blows of star birth and death. This transforms our understanding of these dark clouds. They are not quiet, cold nurseries, but seething, dynamic systems where the turbulent plasma itself becomes a luminous canvas, painting its violent history in shifting waves of invisible light. One repeating burst in particular has offered a new kind of key to the universe's hidden architecture. FRB 180916 does more than just repeat its performance every 16.35 days. Its radio waves arrive in a highly organized state, twisted into a spiral pattern we call strong polarization. This precise alignment is a fragile treasure, a cosmic fingerprint that can only be preserved or altered by the conditions it encounters on its billion light-year journey. The key to reading this fingerprint is a phenomenon known as Faraday rotation. As the polarized radio wave travels through the cosmos, any magnetized plasma it encounters will act like a celestial dial, slowly twisting the orientation of this spiral. The more dense and strongly magnetized the plasma cloud, the greater the twist. By measuring precisely how much the polarization of FRB 180916 has been rotated, astronomers can work backwards. They can calculate the total strength and direction of the magnetic fields that the signal encountered along its entire path, effectively using the burst as a probe to map the invisible magnetic scaffolding of the galaxies and intergalactic space it passed through. This should be a straightforward cosmic measurement, yet when they applied this technique to FRB 180916, the results were baffling. The observed Faraday rotation was far too small, almost negligible. This is the polarization puzzle. For a signal to travel such a vast distance and remain so pristine, it must have passed through incredibly clean, demagnetized corridors of space, avoiding the dense, magnetized plasma halos that are thought to surround most galaxies. This is like throwing a message in a bottle into a hurricane and having it arrive completely dry. How could this be possible? One radical suggestion is that the burst originated in a region of space with a highly ordered but very weak magnetic field, one that applies a gentle, consistent twist that we simply cannot detect. Another, more profound possibility is that our fundamental understanding of these immense plasma halos is flawed. Perhaps they are far more patchy and less magnetized than our models predict, filled with calm voids that the signal just happened to slip through. This single, twisted radio wave does not just tell us about its source. It challenges our map of the cosmos itself, suggesting that the magnetic seas between galaxies might be far more complex and strangely tranquil than we ever believed. The pristine polarization of one repeating burst was a puzzle, but other signals present a far deeper existential challenge. Among the hundreds of fast radio bursts now catalogued, a strange subset emerges, the dark ones. These are bursts pinpointed with incredible accuracy, their cosmic coordinates known to a tiny fraction of a degree. Yet when the world's most powerful optical telescopes, like Hubble, swivel to look at that exact spot, they see nothing. No galaxy, no stellar nursery, not even a faint smudge of light. The origin point is a perfect, empty void, a window into the blackness between the galaxies. A titanic explosion that can outshine 1 billion suns appears to have come from nowhere. How can something so powerful be homeless? The leading theory is as dramatic as the mystery itself. Imagine a supermassive star that lived a fast and violent life in the heart of a dense galaxy. When it died, the supernova explosion that created its neutron star core was so asymmetrically violent that it received a colossal kick, a gravitational slingshot that flung the newborn stellar corpse out of its home galaxy at thousands of miles per second. This is a rogue magnetar, a cosmic cannonball of immense magnetic power, now traveling endlessly through the cold, dark intergalactic medium. But this medium is not a true vacuum. It is filled with a diffuse, superheated plasma, a ghostly fog of ionized hydrogen and helium that stretches between galaxies. For millions of years, this rogue magnetar travels in silence. Then its crust cracks under unimaginable magnetic stress. It unleashes a starquake, sending a shockwave of energy not into a dense nebula, but into the surrounding intergalactic plasma. This tenuous cloud, when struck by the relativistic shock, can still act as a screen for the explosion. The burst is generated right there, in the emptiness, its light coming from the interaction between the magnetar's fury and the only material around, the faint plasma of the void. We see the brilliant flash, but the host galaxy is millions of light years away, completely disconnected from its runaway child. Another, more speculative idea pushes the boundaries of physics itself. What if the burst does have a host, but one that is completely invisible to us? The signal could be coming from a galaxy made predominantly of dark matter, whose ordinary matter was stripped away eons ago. Or the space between us and the burst could be warped by a hidden clump of dark matter. If this invisible mass were concentrated enough, it could act as a gravitational lens, bending the light of a distant, faint galaxy and amplifying its signal, making a faraway burst appear bright and seemingly hostless. The dark bursts force us to confront the limits of our vision. The cosmos is populated not just by what shines, but by what moves through the darkness unseen, their presence betrayed only by the momentary echoes they leave in the universe's silent, plasma-filled oceans. An aging star is literally writing its history across the sky. Mera, a pulsating red giant hundreds of light years away, is not merely drifting through space. It is racing, and as it moves, it sheds its own outer layers in a colossal stellar wind. The Galaxy Evolution Explorer satellite revealed that this wind has been sculpted by its passage into a breathtaking structure, a comet-like tail of glowing plasma and dust that stretches an incredible 13 light years behind it. That is a trail of cosmic breadcrumbs longer than the distance from our Sun to its nearest stellar neighbor. Yet within this magnificent wake, astronomers have detected something far more subtle and puzzling. Superimposed on the tail's gentle glow are faint, periodic signals, rhythmic flickers that pulse with a regularity that echoes the star's own heartbeat. Mera itself is a variable star, brightening and dimming in an 11-month cycle as it expands and contracts. The leading theory suggests that these internal pulsations send powerful pressure waves through the stellar wind. When these waves crash into the denser, cooler plasma and dust of the tail, they could be compressing the material, causing it to glow more brightly for a moment before it relaxes, creating the observed rhythmic flicker. It is like a slow-motion sonic boom traveling down a cosmic corridor, lighting it up section by section. However, there is another, more dynamic possibility. Mera is not traveling through a perfect void. It is plowing through the interstellar medium, a diffuse soup of gas and dust that fills the galaxy. The interaction between Mera's fast-moving tail and this stationary interstellar material could be generating these signals. Think of it as a boat moving through water. The bow creates a wake, but if the water is filled with floating debris, the wake will be choppy and irregular. In Mira's case, the debris is the magnetized interstellar plasma itself. As the tail rams into this material, it could create regions of turbulent shock and electrical currents that release energy in brief periodic bursts. The faint signals rippling through Mira's tail are more than just a curiosity. They are a direct measurement of a star's interaction with its environment, a real-time experiment in how stellar matter is returned to the galactic ecosystem. Each flicker is a clue, helping us decode the complex physics of how the universe recycles itself, one dying star at a time. Deep within the fog of our own galaxy, a faint but persistent glow has resisted all conventional explanation. This is the anomalous microwave emission, a diffuse light that permeates the Milky Way at microwave frequencies, and it simply does not match the signature of any known celestial object. It is not the leftover radiation from the Big Bang, nor is it the predictable warmth of interstellar dust. For years, its source was a perfect blank spot on our cosmic map. The leading hypothesis to solve this mystery points to something astonishingly small, yet ubiquitous. Scattered throughout the vast clouds of interstellar plasma are countless nanoparticles, specks of dust and carbon no larger than a single molecule. These are polycyclic aromatic hydrocarbons, complex carbon chains that are essentially tiny, spinning flakes. When these minuscule particles are caught in the turbulent, magnetized fields of a plasma cloud, they begin to spin at incredible speeds, billions of times per second. And because many of them carry a slight electrical charge, this frantic rotation generates a faint but detectable microwave signal. It is the cosmic equivalent of a trillion tiny electric motors, all humming in unison across the galaxy. This idea elegantly connects the invisible world of quantum physics to the grand scale of interstellar space. The very clouds of plasma that can amplify and distort colossal radio bursts are also host to this subtle, collective whisper from the smallest of particles. Yet, definitive proof remains elusive. The signal is so faint and blended with other emissions that isolating it is a monumental challenge. This pervasive glow reminds us that the universe is structured at every scale, and that some of its most profound mysteries are not written in violent bursts, but in the quiet, collective hum of the infinitesimal. The universe's lighthouses can illuminate more than just the void. A powerful pulsar named Geminga, spinning furiously just 800 light-years away, is one of the brightest sources of gamma rays in our sky. Yet its greatest mystery is not the star itself, but the immense, ghostly halo that surrounds it. This faint, extended glow of high-energy radiation stretches for dozens of light-years, a vast and shimmering sphere centered on the dead star. It is a structure that should not be visible to our eyes or our telescopes at all. The explanation lies in a violent and invisible wind. Geminga, like all pulsars, is not just a spinning beacon. It is a cosmic engine spewing a hurricane of charged particles, a relentless gale of electrons and positrons moving at nearly the speed of light. This pulsar wind does not travel through empty space. It slams into an ancient, invisible cloud of interstellar plasma, a relic cloud of ionized gas that was lying dormant in that region of the galaxy. The collision is one of the most energetic processes imaginable. As the ultra-relativistic particles from Geminga's wind smash into the magnetized plasma of the cloud, they are whipped into a frenzy by tangled magnetic fields. This violent acceleration forces the particles to release their immense energy, not as radio waves, but as the gamma rays we see forming the halo. Think of it as a celestial version of a neon sign. The invisible cloud is the glass tube, and Geminga's pulsar wind is the electrifying current. Without the current, the tube remains dark, but when the wind hits, the entire structure lights up, revealing an architecture we would never have seen otherwise. This ghostly glow is more than a pretty light show. It is direct evidence of a pulsar's immense influence on its environment. proving that these stellar corpses can energize vast regions of space, turning quiet plasma clouds into colossal, high-energy laboratories. The halo's exact size and shape remain a puzzle, hinting at a turbulent and complex relationship between the pulsar's focused wind and the chaotic, magnetized sea it is trying to push aside. For decades, the lighthouse model for pulsars has been a masterpiece of cosmic elegance. A spinning neutron star with its beam of radiation sweeping through space like a beacon from a distant shore perfectly explained the metronomic pulses we observe. But the universe adores complexity, and this beautifully simple model is beginning to crack under the weight of bizarre, real-world data. Certain pulsars are behaving not like steady clocks, but like faulty machinery, glitching in ways that defy our cleanest theories. Take the Vela pulsar, a cosmic timekeeper famous for its regularity. Without warning, its spin rate can suddenly increase by a tiny but significant fraction, a glitch that happens in an instant and then slowly decays over months. These are not minor hiccups, they are fundamental seizures in the stellar engine. The standard lighthouse model, which pictures a perfectly rigid, spinning sphere, cannot easily account for such a violent and sudden speed up. The explanation seems to lie not in the star's solid crust, but in the chaotic ocean of plasma that is its magnetosphere. Within this seething soup of superfluid neutrons and charged particles, a sudden and catastrophic instability can occur. Think of it as a cosmic avalanche. The interior of the neutron star, a superfluid, is normally decoupled from the solid crust. But if a vast internal layer of this superfluid suddenly unlocks and transfers its immense rotational energy to the crust in one dramatic event, the star would experience a glitch. This is the star literally catching up with itself, a reconfiguration of its internal plasma dynamics that manifests as a jump in spin. Another pulsar, known as the Crab pulsar, presents a different puzzle. It not only glitches, but its pulses sometimes change shape entirely, as if the lighthouse's lamp has been swapped for a different bulb. This points directly to a reconfiguration of the plasma at the pulsar's magnetic poles, the very region where the beam is generated. The plasma in this area is not a passive gas. It is a turbulent, magnetically confined structure that can exist in different stable states. A small shift in the flow of charged particles or a sudden rearrangement of the magnetic field lines could cause the entire emission region to flip into a new mode. The beam's shape and intensity would change instantly, not because the star itself has changed, but because the plasma lens focusing its energy has suddenly snapped into a new configuration. These glitches and mode changes are more than mere anomalies. They are vital telemetry from the most extreme physical regimes in the universe, telling us that the elegant lighthouse is in reality a turbulent, unstable, and deeply dynamic entity. The steady pulse we rely on is a fragile illusion, maintained only until the next plasma avalanche within the star's heart reshapes the beacon we see from Earth. Even our boldest explorers have been caught off guard by the plasma sea. The Voyager probes, humanity's farthest-reaching spacecraft, sent back a stunning revelation as they crossed the final frontier, leaving the protective bubble of our sun and entering the true interstellar medium. The boundary was not a calm, silent shore, but a place of turbulent and unexpected waves. Voyager 1, after its historic exit, detected a series of massive, rolling oscillations in the surrounding plasma. Scientists called them interstellar tsunamis. These were not waves of water, but colossal pressure waves propagating through the ionized gas of the galaxy, enormous ripples that made the local plasma density surge and fall dramatically. The sheer power and repetition of these events was a complete surprise. Our models predicted a relatively smooth transition, but the reality was a complex and stormy interface. The leading theory suggests our sun's own magnetic influence is the cause. As our entire solar system moves through the galaxy, the heliosphere, the vast bubble carved out by the solar wind, plows through the interstellar plasma like a ship through a magnetized ocean. This motion likely creates a bow shock, a turbulent region where the two competing plasma environments collide and mix. The interstellar tsunamis could be the reverberations from this ongoing collision, the cosmic equivalent of the bow waves sent out by a moving vessel, but on a scale encompassing our entire solar system. Each tsunami wave is a direct measurement of this hidden interaction, revealing that the edge of our cosmic neighborhood is a dynamic and chaotic place, constantly reshaped by pressures we are only beginning to feel. A dragon's egg has hatched in the depths of space, and its whisper is rewriting the rules of stellar life. The NGC 6164 and 6165 nebula, a magnificent bipolar structure, unfurls across the void like the wings of a cosmic serpent. At its heart lies a ferociously hot, massive star, and for years, astronomers believed the nebula's beautiful shape was a simple story, sculpted solely by the star's own powerful winds. But recent radio observations have detected a faint, structured emission within the nebula that tells a different, more complex tale. This radio whisper does not perfectly align with the predictable flow from the central star. It has its own intricate patterns, its own ghostly geometry that suggests something else is at work within the churning plasma. The star's wind is like a hurricane, but this radio signal is the fingerprint of something moving within that hurricane, an unseen hand stirring the pot. The leading theory points to the nebula's complex magnetic fields. The plasma within the dragon's egg is not just a hot gas, it is a magnetized fluid, and these magnetic fields can become twisted and braided by the star's rotation and the turbulent motions within the nebula itself. In regions where these field lines become impossibly tangled, they can snap and reconnect, a process that acts like a cosmic generator, accelerating electrons to near light speed. It is these frantic electrons spiraling along magnetic field lines that generate the specific, structured radio whisper we detect. This subtle signal is evidence of a hidden energy source, a process of magnetic transformation occurring within the plasma cloud itself, independent of the brute force of the stellar wind. It reveals that a nebula is not a passive sculpture, but a dynamic, energetic entity with its own internal life and its own invisible magnetic heartbeat. These faint echoes of interstellar plasma point toward a far grander cosmic secret, a hidden architecture that holds the answer to one of cosmology's most profound puzzles. For decades, scientists have known that a vast portion of the universe's ordinary matter, the stuff that makes up stars, planets, and us, is simply missing. When we tally up all the matter we can see from the dawn of time, there is a staggering gap. A full 30 to 40% of the expected ordinary matter, known as baryons, is unaccounted for. It is not dark matter, but the very atoms that should be visible, and their absence threatens to undermine our most fundamental models of the cosmos. So where did it all go? The leading suspect is not a place, but a state of matter. Theorists believe this missing material is woven throughout the universe in a ghostly, tenuous web known as the warm-hot intergalactic medium, or WIM. This is not a cloud you could see or touch. It is a colossal network of filaments, a cosmic spiderweb made of superheated plasma, with temperatures ranging from hundreds of thousands to millions of degrees. This gas is so diffuse and so incredibly hot that it does not emit light in a way our telescopes can easily capture. It is the universe's most perfectly hidden reservoir, a fog so thin and so bright with heat that it becomes functionally invisible. How do you find something that is everywhere, yet gives off almost no discernible signal? The answer lies in the very distortions we have been exploring. The faint, diffuse signals from this plasma web are not bright beacons. They are subtle imprints, tiny fingerprints left on the light that passes through it. When the brilliant light from a distant quasar travels billions of light years to reach us, it must pass through these filaments of the WIM. The superheated plasma in these filaments contains highly ionized atoms of oxygen and other heavy elements. As the quasar's light passes through, these ions absorb very specific tiny amounts of energy, creating minuscule dips in the quasar's spectrum. Finding these absorption lines is like looking for the unique shadow of a specific needle in a cosmic haystack. It requires immense patience and the most sensitive space telescopes like the Hubble to even have a chance. Another method is to look for the faint, soft X-ray glow that this hot plasma might emit, but this signal is incredibly weak, drowned out by brighter sources. The challenge is monumental, but each unexplained, faint signal we detect from the void brings us closer to mapping this hidden ocean. The missing baryons are likely all around us, woven into the fabric of space itself, their presence betrayed only by the ghostly whisper of a plasma so hot and so diffuse it has eluded us for a generation. Finding them would not just solve an accounting error, it would complete our map of the ordinary universe. The galaxy NGC 6946 has earned a dazzling nickname, the Fireworks Galaxy, for its spectacular record of stellar explosions. Yet amidst its frequent supernova, astronomers have spotted a different kind of flash, brief and brilliant flares that appear and vanish without the cataclysmic aftermath of a dying star. These are not the final breaths of giants, but something far more peculiar, like fireflies blinking on and off within a cosmic bonfire. The galaxy's spiral arms are thick with dust and glowing plasma, a perfect hiding place for a specific and violent type of object, a microquasar. Imagine a stellar black hole or a neutron star locked in a tight orbit with a normal star. As it voraciously feeds on its companion, it doesn't just swallow the material, it funnels some of it into incredibly powerful, focused jets that scream away at nearly the speed of light. These jets are not made of light, but of superheated, magnetized plasma. When one of these relativistic plasma jets plows directly into a dense cloud of interstellar material within the galactic arm, the collision is devastating. The impact creates a shock wave that heats the cloud to incredible temperatures, causing it to flare up brilliantly across multiple wavelengths for a short period before fading away. It is the cosmic equivalent of a blowtorch suddenly igniting a pocket of gas, a brief, intensely bright flash born from the interaction between a focused beam of plasma and the raw material of the galaxy itself. These transient flares are more than just strange lights. They are the intermittent beacons of hidden monsters, feasting in the dusty lanes of the Fireworks Galaxy and occasionally announcing their presence with a sudden, deceptive spark. The ultimate fate of these cosmic whispers may rest with a silent forest of antennas rising from two continents. The square-kilometer array is not merely another telescope. It is a fundamental shift in our ability to listen to the universe. When its thousands of dishes and antenna stations across South Africa and Western Australia become fully operational, it will form a single, colossal ear with a collective collecting area of, as the name suggests, 1 square kilometer. This is not just an incremental improvement, it is a leap in sensitivity that will make our current most powerful radio telescopes seem like primitive hearing aids by comparison. This immense power is not aimed at making loud signals louder, but at detecting the impossibly faint. It will allow us to hear the subtle symphony of interactions between radio waves and the interstellar plasma they travel through. Every single one of the signals we have explored, from the briefest fast radio burst to the most puzzling planetary candidate, carries within it the imprint of every plasma cloud it has ever passed through. The SKA will be able to read that imprint with the precision of a master decoder. It will measure the Faraday rotation and dispersion of these signals with such fine detail that we can essentially perform a cosmic tomography, mapping the density, turbulence, and magnetic field strength of the invisible plasma filaments along billions of light-years of path. It could finally tell us definitively if the wow signal was a natural whisper magnified by a plasma lens, or if it truly was something else. It could trace a dark FRB back to its rogue magnetar home in the void, or reveal the calm, demagnetized corridors that allow some signals to arrive so pristine. This unprecedented sensitivity will undoubtedly solve long-standing mysteries, but its true legacy will be in the new questions it forces us to ask. By listening so deeply to the quietest parts of the cosmos, the SKA is guaranteed to discover entirely new classes of signals, phenomena so faint and strange we do not yet even have a name for them. We are on the verge of hearing the universe not just shout but breathe, and in that breath we will find a whole new layer of mystery waiting. These 25 cosmic whispers, from the singular wow signal to the silent dark bursts, form a grand and puzzling symphony. Their stories are wildly different, yet a common thread weaves them together. Each one, in its own way, has been touched by the invisible ocean of interstellar plasma. This turbulent, magnetized gas is far more than empty space. It is the universe's great deceiver and its most brilliant amplifier. It can focus a faint whisper into a shout we mistake for contact, generate a boom of cosmic thunder from a black hole storm, and sculpt the death cry of a star into a fleeting, brilliant flash. It can cloak an entire star system in radio silence and make our most reliable cosmic clock stutter and fail. Plasma is not merely the backdrop for these mysteries. In many cases, it is the active participant, the very engine of the phenomenon itself. This realization is both humbling and exhilarating. We have mapped the stars and the galaxies, but we are only beginning to understand the chaotic, dynamic sea that flows between them. The true message of these 25 signals is not that we are alone or that we are not. It is that the cosmos is infinitely more complex, more subtle, and more clever than we ever imagined. Our search for intelligence continues, but we are simultaneously learning to listen to the universe itself, to the hidden language of its storms and its silent, simmering power. So we turn this final question to you. Of all these cosmic riddles, which one captures your imagination the most? Is it the ghostly echo of the wow signal, the violent repetition of a magnetar's cry, or the profound silence of a burst from the void? Share your favorite mystery in the comments below, and let's continue this journey of cosmic curiosity together.